Good afternoon, class. My name is Andrea Lerma, and I'm going to be presenting the art gallery problem. Okay, some things that we're going to be covering throughout this presentation is going to be polygon triangulation, the ear clipping method, which is the 2 years theorem that we cover in class, the three colorable method, and we're going to be also talking about orthogonal polygons. So in 1973, the geometer and topologist Victor Klein from the University of Washington posed an innocuous looking problem. The art gallery problem in which cards, cameras can only be placed on the vertices of the polygon P representing the gallery. Chabato in 1975 found that it is occasionally necessary and always sufficient to have n divided by 3 cards or cameras to cover an n vertex polygon. So the question is, how many cameras do we need to guard on a given museum, and how do we decide where to place them? So the first thing that we need to do is polygon triangulation. So triangulation of a simple polygon P is the composition of P into triangles by a maximal set of non-intersecting diagonals. Every convex polygon admits a triangulation, and any triangulation of a convex polygon with n vertices consists of exactly n minus 2 triangles. Triangles in a valid triangulation should not intersect each other. The reason that I'm including that side note on this slide is because when we were doing one of the assignments in the class, I made that mistake. When I was triangulating on a polygon, I included 2 triangles that were intersecting. So of course, that's not the correct way of doing polygon triangulation. So that note is just, it's for me, but it also could be helpful for you to have it in mind when doing triangulations. Okay, so then the next method that we have is the ear clipping method. One way to triangulate a simple polygon is based on the fact that any simple polygon with at least 4 vertices without holes has at least 2 ears, which are the triangles with 2 sides being the edges of the polygon and the third one complete inside it. And the theorem that we covered in class was, except for triangles, every simple polygon has at least 2 non-overlapping ears. We were able to prove this by mathematical induction in the class, and I did not include that, but we have covered that before. So this example is the 13 vertex polygon. So as you can see, we have 13 vertices. So the first thing that we need to do is triangulate the polygon. So I'm gonna be showing you the way that we're gonna be triangulating this polygon. So we have 1 triangle, 2, 3, 4, 5, 6, 7, 8, 9, 10. So as you can see, we have 11 triangles, which is true from the formula that we had before, which is n minus 2, 13 minus 2 is 11. Okay, so then once we did the triangulation, we're gonna go with the next step, which is the 3-colored method. The vertices of the polygon are then 3-colored in such a way that every triangle has all the 3 colors. Once a 3-coloring is done, the vertices with any one color from a valid guard set, because every triangle of the polygon is guarded by its vertex with that color. Since the 3 colors partition, then n vertices of that polygon, the color with the fewest vertices forms a valid guard set with the most guards. So the next step, once we did the triangulation, we're gonna do the 3-color method. So I choose the colors blue, green, and pink. So we're gonna be doing that in all the vertices, and as you can see, each triangle in the polygon has all the 3 colors. So that's very important to have in mind when we're distributing all the colors. And then we're gonna count the one with the least number of points, right? Like the blue one has 5 points, the green one has also 5, and then the pink one has 3. So we're gonna go with the least, so which is the color pink. So we're gonna choose points C, F, and I. And then what we're gonna do is that we're gonna be shading the colors that that camera C is going to be covering in the polygon. So we have again the points C, F, and I. So camera C is going to be covering the triangle ABC, this next triangle, and all these ones. So then we move to the camera F, which is going to be covering the triangle FGE. And then the last one is triangle, the point I, which is covering triangle GIH. So the next one. So we're going to be talking about orthogonal polygons. In an orthogonal polygon, its edges meet at right angles. The lower bound of n/3 guards cameras no longer holds for the orthogonal polygons. So any orthogonal polygon can be decomposed into convex quadrilaterals, which induce a fourth coloring of the vertices. So as you can see, we're gonna be doing the same process that we did with a convex polygon, but the only difference is that we're not gonna be doing triangulation, we're gonna be decomposing it into quadrilaterals. And instead of being 3 colors, we're gonna be doing 4 colors. So we are doing the same steps in the same order. So then from this, the orthogonal art gallery problem provided originally by Kahn, Clow, and Clayman says that n/4 cameras or guards are always sufficient to cover any orthogonal polygon with n vertices. I'm not gonna go over into detail with this theorem, but I'm going to include a PDF that contains the proof of this theorem. So if you wanna check, it's pretty simple and straightforward. And it has a lot of information. Some of the things that I did not mention on the presentation about orthogonal polygons, you can find it in there. Okay, so let's suppose that we have a restaurant, right? And we wanna cover all the areas of the restaurant. And we need to see, again, the same thing. Instead of being an art gallery, you can be creative and just think whatever you can cover with the cameras. Of course, you don't want to use a lot of cameras. We're going to be doing the same process. Now, the first thing that we're going to be doing is the composition of the orthogonal polygon into quadrilaterals. So this is what I did. Then we partition everything into quadrilaterals. Then once we do that, we're gonna be coloring. As you remember in the triangulation, each triangle had the 3 different colors. It's gonna be the same thing with this one. If you notice, each quadrilateral has the 4 colors. And again, we're gonna count the one with the least number of the least number of points, and those are the ones that we're gonna be choosing. So in this case, the blue points were the one that has the least number of points. So we're gonna go with that one. So this this blue point is gonna be covering this area, then this area, and then we're gonna move with the next point, which is this one. And it's gonna be covering that quadrilateral, then this one, and then that one. And then we're gonna move with this quadrilateral right here. It's gonna be covering that area, this region, and then we go with the next one, which is gonna be this one right here, which is that one. So if we were to open a restaurant and we wanna cover all the areas in the restaurant with this orthogonal shape, with this polygon, we're gonna be only needing 4 cameras. So the art gallery problem has a lot of application, especially in, well, this is part of, this art gallery problem is part of the geometry computation geometry, and it has a lot of applications in robotics, robotics design, and all these other applications. So thank you for watching me, and if you have any questions, please let me know.